anyway, just recall, all right, Trojan Equation, this and that, hopefully you're okay with that. A wave function squared is a probability density, so it has no meaning unless it's integrated. The point 2, the eigenvalue equation is this, and that's all fine and good. If it doesn't work, whatever your model problem is, probably check your math, number 1. Number 2, you're getting, your analysis is yielding mathematical junk. So we brought up the example of a wave function. So we have multiple, remember this works for any operator, including the Hamiltonian operator. Hamiltonian is special because it yields energy, and we think of the wave functions as being real. Now the reason that is that you can calculate differences in energy levels using the Hamiltonian, and your spectroscopic observables will yield that information. So that's why we think of them as real, because, I mean, I'm not trying to sound too funny here. Literally, that's what you see. Right? So, so we brought up cosine as a good wave function for a Hamiltonian, a free wave Hamiltonian, but when I applied that to momentum, it failed. Right? So that's point number 2, is that wave functions of a Hamiltonian may not be eigenfunctions of another operator. Notice I was actually very careful with my language. Wave functions for Hamiltonians, eigenfunctions for other operators. I'll be careful about that. Energy, any eigenvalue. The solution is, if that doesn't work, then you do expectation values. And actually in some textbooks, they don't even, for some like lower level undergrad textbooks, they don't even show the eigenvalue equation. They just show expectation value. Expectation value will almost always work. Actually, I believe it will always work. So you can imagine why show this and have to explain the nuances of like what I just described, of wave functions may or may not be okay with other operators. That sucks. But anyway, and then remember the last thing I mentioned, which is that the reason that this works, and this is explained in my silly textbook, is that if you're talking, like we're working in one dimension, right? We're working in X. So if we're working in X, a wave function can be decomposed into a linear combination of the eigenfunctions of another operator. So the example was momentum is okay with e to the ikx, e to the minus ikx. It was not okay with sine or cosine. But sine or cosine is e to the ikx plus or minus e to the minus ikx. So that's why you can calculate momentum of a sine or cosine because of this property. And again, that's in my silly textbook, so look at that as, I mean, that's the answer, but if you're a little confused, my little textbook explains it in a little bit more detail. Remember that the Trojan equation is linear, and I just used that example of you can have wave function. Remember I mentioned that every operator, the wave function, its eigenfunctions, there's usually an infinite number. Because usually these are like ground states and excited states, and there's usually an infinite number of excited states. Corresponding energies, corresponding momentum. But it turns out summations of those same eigenfunctions are eigenfunctions. And we're going to use this a lot. I mean, I did that right here. It's the same, I'm stating the same thing. Anyway, fourth was separability. And I didn't mention this last time. Let's say the Hamiltonian operator. Now, this is when you have more than one dimension. Sorry, that's annoying. When you have more than one dimension, it turns out that, I know I gave this long-winded thing. I gave a long-winded explanation of separability, but it really works like this. When the Hamiltonian has its dimensionality, like ddx plus ddy, ddr, dd phi, right, for spherical or cylindrical coordinates. when they're like a bunch of terms plus a bunch of other terms, dimension 1 plus dimension 2, then the wave function will, the total wave function will be 1 for x times 1 for y, right? As opposed to like sine of x plus y, that doesn't fit this mold. Sine of x times sine of y, that does, that's what this is. And it also gives us a way to solve those little dimensional wave functions by miniature Trojan equations. And again, we talked about that last time. But that ends up being really important. So anyway, it's really rare. I believe in any example that's physical, that's like, I can make up operators that are crazy, but they don't really describe anything real, so why would we do those problems? When I describe operators, Hamiltonians usually, and they're describe something real, they'll be separable. Now, the hydrogen atom Hamiltonian, it's actually kind of hard to see that. It's really, the fact that it works like this is a little obscure, and you have to kind of tease it out. So understand that separability may not be so obvious at times. And we'll see that, we'll actually see that kind of soon. We're going to do a particle in a sphere. Not a particle in a box, a particle in a sphere. It's way harder. Particle in a box, particle in a cube. Particle in a box is easy. Particle in a cube is also incredibly easy. Think that cube is sphere, blows your head off. That's how it is. Anyway. Okay, so that's, again, I'm still reviewing. So now let's start getting to 1D wave mechanics. And you have 2 problems on your homework that this is related to. So I'm going to do these on, this is called an analytical solution. Your homeworks at times will be numerical, like that you have to write that one program to simulate an XRD, and that's all about waves and matter. That's why I want you to do that, get that in your head. Plus, so many of our groups are material scientists that you're probably going to be looking at powder XRD. So this is like a good thing for you to do to understand powder XRD. And again, the lessons are waves and matter. And so you're going to do some programming there. The next programming job you have is going to be looking at these flat potential surfaces and solving the Trojan equation for flat potential surfaces. I'm going to do pen and paper in class, and I think maybe Friday, maybe Wednesday or Friday, I'll actually do a computer example. And you will too when you're home really soon. I think next homework. Okay, so this will be a free wave, and that just means we only have one dimension, and that's a wave function. Potential energy is 0. One-dimensional universe with nothing in it except, I don't know, an electron. Or maybe a quark, but who cares? Anyway, it's by itself. Ridiculous problem. But the purpose is to make you learn diffie-qs. So we're going to do some diffie-qs. Minus h bar squared over 2m, double derivative of the wave function, which of course only has x in it, is equal to the energy times the wave function. So I want to do this because we're not going to be solving differential equations too much, but it ain't 0 either. Especially today, I am showing you this diffie-q. How to solve this diffie-q. That's today's lesson. And you got actually, I think your 3rd or 4th homework, one of them. No, more like 5th. Anyway, I forgot. You got a really good diffie-q. I'm going to make you do it again. I'm going to make you solve a diffie-q. I forgot what problem, but anyway, it's actually kind of interesting. I show another interesting way to solve this. We'll also do diffie-qs on computers, which I like better. Okay, so anyway, this is the Trojan equation with no potential. I'm defining k squared. Now remember, k squared is, this would be 2 pi over lambda, so that's k squared, so that's 2 pi over lambda. But the Trojan equation reveals that it's also 2me over h bar squared. So notice that you can solve the wavelength, the de Broglie wavelength for whatever type of quantum system you're describing via a relationship like this, whatever. What this allows me to do is to simplify this in the following manner. Now, one thing is that wait, is that? Oh, yeah, it's plus because there's a minus. I bring the minus sign over, and then anyway. Notice I just simply I multiplied through by 2m over h bar squared minus. I multiplied through, and then I had k squared over here minus k squared, so then I brought it over to the left. Now the reason is that Diffie cubes look like this. When you look these up, if you have this Diffie cube to solve, you can Google it and you'll find this. It'll look just like this. So I want you to see what they look like when you try to look them up, because that's how I solved it. Okay, so we're going to solve this. And to solve it, we're going to back off of it for a while. Let's do some basic Diffie cube. Yeah, that's the thing about the Schrodinger equation. It wouldn't be nearly as hard if it wasn't for kinetic energy. If it wasn't for that, this would actually be really easy. But it's a double derivative. If you switch coordinate systems, it's still a double derivative. In other words, if you're working in spherical coordinates, it's still a double derivative. You can never avoid it. As soon as you got a double derivative, you got a differential equation. That is a differential equation. Okay, now how do we solve Diffie cubes? This is the first example you'll learn in class, and I'm going to use proper mathematical notation, because again, this is what you find. Okay, so dy dx plus c of x is equal to 0. This would be first day of Diffie cube class, which I don't know if you guys had Diffie cube. All right, when I was in college, that was the last math class we were required to take. You folks?
Yes.
You know? Okay, so for the most part, no. Yeah, now STEM, science, technology, engineering, math. Not math, okay. Everyone but math. When I was in college, we had to take Diffie cube. But I noticed that they stopped doing that. Now you just have to go to Cal 3, which anyway, I think is kind of. I didn't like Diffie cube too much. I was unsatisfied with it, and I'll explain why. But anyway, okay, so let's work on this. Okay, the first thing to do, I now notice that y is actually a function of x. So don't lose sight of that, right? I'm kind of, instead of y, I should write f of x. I should probably do that, but for various reasons, I like to express this function just with the letter y. One reason is that what I can now do with this, so the next step, is I like to juggle things around. So, and this also shows you a partial. Partials are meaningless by themselves, but a partial divided by a partial is a derivative. A partial by itself is meaningless, but it could be integrated. So notice that I'm treating partials like its own object, its own mathematical object. It is. Now, when you took Calc 1, you always saw a derivative expressed this way, so it's like it has to look this way. But I'm telling you, no, it's not. It's really A over B. And just like A over B is equal to C, I can rearrange that, and A is equal to B times C. So I can manipulate these at will. Okay, a calc identity that hopefully you're aware of. This is the derivative of a function over itself is the derivative of the natural log. Okay, and then you simply integrate it. And of course, notice that limits have the same form as the partial. So let's think lower limits x equals 0 and ln y equals 0. Upper limit is x, and upper limit over here would be ln y. I always thought that was clever. So ln, integrated partial, it's just what's the partial, right? Minus c. So am I doing this right? I'm kind of just writing minus cx. Now I'm assuming that c is a constant. That's reasonable. And therefore y is not e to the y is e to the minus cx. There we go. All right, so stupid, right? Stupid easy. Again, you would learn this the very first thing in DiffyQ, first day DiffyQ. And then you think that you can do this from now on. You're like, oh, this class would be easy. No. So this is a first order, I believe, is this inhomogeneous? I can't remember. Yeah, this is inhomogeneous because it's equal to 0. If it's not equal to 0, then it's equal to 0. Diffy stuff, 0. Homogeneous, not 0. Inhomogeneous. Inhomogeneous is awful. Homogeneous, usually these are easier. Just so you know the terms. That's not important. It's just that's the correct mathematical term. I just want you to know what the correct mathematical term is. Okay, now while everything seems easy, now let's do this double derivative. Double derivative. Now here's the damnedest thing. You think like, oh, well now we'll just have to bring dx over twice and integrate twice. No, you can't. Yeah, that actually will not work. That does not work anymore. So it seemed like that trick was like, oh, I'll just use that trick from now on. No, it only works in that first order. This is second order because I have double derivative. Double derivative is second order, single derivative is first order. Don't worry about that. I'm not testing you on if you remember these math notations, but I do want you to hear this stuff to know that that's what this stuff is. Okay, all right, now what do you do with this? So this is a bit more complicated. All right, first step, now get this is muddy. You're going to make it more complicated. I'm going to take this, sorry, what am I doing with parentheses? Oh, I need a parentheses, that's why. Okay, notice that I am complicating it. Why in God's name did I complicate it? What I've done is I've kept dy squared dx squared. A is 1. But yeah, I can keep it. A is 1. There's no problem with that. B dy dx. B is 0. So why is it there? You'll see. Cy, that's still there. Still equal to 0. Okay, I've complicated it. Okay, but hopefully you recognize, although it's a little hard to see at first because you've got derivatives. Yeah. Something squared plus something plus a constant is 0. That's a quadratic equation. Very good. Clever, isn't it? Okay, quadratic equation, we want to factor it, right? So remember, quadratic equations can be solved using b squared plus or minus. You learned it in middle school. Oh yeah, but the other thing is though you want to actually, in this case, you want to factor it, right? What foils, right? A plus b times a plus b, a b, b, right? What foils to this? Okay, now this actually ends up being a little bit complicated. What you're going to do is you're going to make these dummy variables, and if you want, you can prove to yourself that this works. So what I'm doing is I'm defining alpha and beta this way. The reason I'm doing that, and so you can figure out what alpha and beta are. I don't remember off the top of my head, but with alpha and beta defined in terms of x, in terms of a, b, and c, you can prove this. You can factor it, right? It's a quadratic equation. Quadratic equations come from something that's been foiled. And here's what it is. Okay, so so then multiply this out, double derivative, it will work out. Right? Double derivative, then then AB. Plug in these definitions and it will factor into this. Okay, the point of this is to show that a second order differential equation can be solved with a first order differential equation. These are basically what we dealt with before. So therefore, a solution is going to look like this. E to the minus, let me make sure I get this right. E to the minus, no, E to the minus, E to the R x. R may be negative. We'll figure that out. Okay, so like last time we figured out that exponentials were the solution to this, so I'm just using that. Now I think I had minus cx. R can be negative. I'm making it as generic as possible. So again, I'm going to assume a solution of this form, a solution that's correct for a first order differential equation for a second order, because I factored the second order into two first orders. Ooh, anyway, if that's what we did. Okay. Now, God, I hate to do this to you, but this is why I don't like this board. Let me wipe this out because I'm going to need to plug. I need to plug this into here. Okay, what do we get? Okay, what's the double derivative of this? You should be able to do exponential derivatives in your head. All right, there we go. R squared, and the function remains. But you know what? You know what I noticed is that the function is common to every term, so I'll just factor it out. See how I did that? You know, R function, R squared function, so I just factored the function out because it's R function factored out. That times that. Anyway, just factor it. Okay, now is that 0? Now one of these two things is 0. Which one is it? Yeah, this part. So, yeah, this has to be 0. That's never 0. It's impossible for that to be 0. So this has to be 0. And quadratic equation again. What is R? Middle school.
R is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a.
Yeah. You still haven't memorized. Even if you're headed to middle school, all that over 2a. There we go. We got two solutions, so that's a little funky, but we'll have to deal with that. Let's see what it really is, though. So remember, we're actually trying to solve this. I told you I was complicating it. Let's decomplicate it now, because b is 0, right? If we look back at here, immediately b is 0. There's no, that term isn't there. So b is 0. A is what?
You said 1.
1, and c, of course, is c. so that we can't really. Oh no, wait. Oh, sorry. It's k squared. Yeah, sorry. Let's look at this guy. That's what we're really trying to solve, right? Now I can get back here. Okay, so R is 0 plus or minus 4ac 4k squared. Oh, minus over 2. Okay, so square root of 4 is 2. Okay, so square root of k squared is k. Plus or minus k? Is that right? I. Uh-oh, I got an I. Okay. So therefore, based on that, the wave function is don't forget the x, right? That's what r is. The solution is e to the rx, and r is plus or minus 9kx. But you know what better yet? Let's use that property of you can add these together. There you go. All right, so that's the solution to the free wave problem. And for various reasons, it can unfortunately get a little bit more complicated because depending on the nature of the potential surface, we're going to need constants in front of them. You would need a constant to normalize it for one. But unfortunately, there are other nuances can appear in the potential surface such that you might need to do some balancing of A and B, not only to normalize the thing, but also to account for variations in the potential surface. One reason is that, so remember, we're doing flat potential surfaces, and as I mentioned, this is a free wave. So it looks like this, right? I just drew a line. However, it turns out that this is still a solution for this. You can have steps and still have this be the solution, as long as when you take a step, it's flat. I can even do this, I can even do that, on and on and on. As long as, you know, steps are okay, but as long as you're still flat within whatever step, left or right, this is still the solution. So when you have this jazz happening, A may not be equal to B anymore. So heads up on that. We're going to do some problems starting now, but I want to do one thing about normalization. Now, as usual, we often have some trick to solve these, but they're never normalized. DiffyQ doesn't care about normalization. Actually, they do and they don't. When you solve DiffyQs, and often you would do this in the context of an engineering problem, there's an initial condition. It's actually similar. You notice how, for a first order differential equation, what I did at the very beginning, I solved it with an interval, right? A boundary condition is the same as the limits on the interval. It says that at time 0, the cat was in the house. So that establishes the limits of integration. When you have higher order DiffyQs that are much more difficult, those boundary conditions, there was no interval, right? I didn't see an interval when I solved this. So the boundary conditions then have to be applied after you get the function. Now, again, I'm speaking in terms of engineering mathematics, which is not this class. For us, after you get the solution, it usually needs to be normalized. So that's like our boundary condition. One boundary. We actually have a bunch of them anyway. Okay, so we gotta normalize it. So now recall that normalization. So we need to multiply this by a normalization constant, where the normalization constant is 1 over the square root of the integral of the absolute value. Now remember that the reason that this is that because the wave function squared when you integrate a wave function squared, which is a probability density, you integrate it over all space. That's my generic expression for dx, dy, dz, or whatever the problem is. And you integrate it over all space. You better get the number 1. And that means that the particle is somewhere. It is certainly somewhere. That is how you interpret this. Now, to make this happen, you may notice that a normalization constant of this is going to work out quite well, because what this is notice that Let me put a little n there for normalized. So that means that you have this. And what does that equal? Here I should see how remember this is? Right? See the normalization, you get one of these for every wave function, n squared. So the square root goes away, and so you're just left with the integral over the integral. So of course that's equal to 1. So it's normalized, but that's your normalization constant. All right, so again, I hope that's a childlike EP, right? Okay, let's do this thing, and you're going to throw up on yourself when you see this. Hopefully you see it coming already. Sine star sine, and I will use simply a wave function, which is, what am I going to do? E to the I kx. So let's call it E to the I kx. There's no reason not to do a simpler one. Okay, so dx minus infinity to infinity, because I'm not stipulating that there's anything else going on. Look familiar? There you go. Okay, there's yeah, so this of course is a delta function, the 2 pi delta function. Okay, it's a little funky because it's like k minus k, right? Actually, I should put a little prime by one of these, but I don't know that I can justify that. So this is a convention. I have to admit, I was reviewing my notes. There's one thing that kind of bothers me about this. I don't think this is really correct. So therefore, the normalization, it's the square root of all this. And now you folks know that a Kronecker delta, right? This is covered in your homework. We're going to do this a lot. So this makes sense because if these are not the same thing, right? If they're the same thing, then they cancel each other, right? This is e to the 0. So I'm integrating the number 1, which will go to infinity real quick. All right? If these k's are not the same, I've drawn them the same, but let's say they weren't, then what you've got is an interference pattern, sine times cosine. And it will gain value, lose value, gain value. It depends on what the limits are. And unfortunately, infinity is not defined. So we would just call it 0. It's just defined as 0. Okay. Now with that said, I just want you to know that although I think this is actually incorrect, the way people define a free wave function is they just kind of forget the Kronecker delta and they just keep the 2 pi. Okay. So here's the thing. This actually isn't true. It's really 1 over 2 pi infinity. Now the reason is that, I mean, look at it right here. This is 1. So I'm integrating from minus infinity to infinity dx, which is infinity. The problem is that we can't really put that down and do anything with it because the wave function becomes 0. It's a problem with the model. Like free wave models are great, but they have a flaw, which is that if the universe is truly infinite and a particle is somewhere in that infinite universe, it's simultaneously nowhere. The probability of finding a particle right here in an infinite universe is 0. It's somewhere, but the odds that it's here is 0. Such a low number that I can't comprehend it as being anything other than 0. So because of that flaw, people just say that the normalization is square root of 2 pi. So just heads up on that. I really, it bothers me to no end because I want everything to be mathematically perfect, and this is clearly wrong. But this is the convention. And I also wanted you to see the Quadratic delta again. Okay, so now back to flat potentials. Okay, let me go over here. So let's go ahead and start doing a few examples. And you're starting out with one simple one on your homework, which is just a step potential. And then you've got that double finite well, which is a nightmare. And that's probably what we'll spend most of our time on in the review session. Because there's a trick. There's a trick at the very beginning, and if you don't know the trick, if you get confused about the first step, you'll never get anywhere. You have to get the first step right, and there's a trick. So that's why we need to have these review sessions. Okay, anyway. So for flat potentials, and I'm just going to use this thing. It can be crazy, right? So it's okay if it's crazy. Now the Trojan equation looks like this. What I'm going to do is bring over the B. So there you go. So for the most part, you can see that the potential energy simply sucks energy out. So if a particle hits a barrier, all that's going to happen is it's going to have less energy, less kinetic energy. In a flat potential with no potential at all, it has energy, therefore it's kinetic energy. There's no potential energy. So if it moves into a region of potential energy, it has to lose some of its kinetic energy. And it's losing that much. That's its new kinetic energy. It just has less energy, right? So this is stupid easy. If the energy is greater than the potential, then all we have is for a solution A e to the I kx plus B e to the minus I kx, where again, A and B you need some kind of constants due to normalization. If it's a completely flat potential, it's 1 over square root of 2 pi. For dumb conventional reasons, it actually really wouldn't be vigorously mathematically correct. I still don't know why we're okay with that. But and when you've got some steps and some other steps, A and B might be a little bit more nuanced, and we're going to cover that in a minute. Now, of course, K is simply 2m e minus b over h bar squared, square root of. Notice that I actually had it weightier here and less weighty there. I increased the wavelength. Remember that K is inversely proportional to the wavelength. So if K gets smaller because some energy gets shaved off, then the wavelength gets longer, inverse. Smaller K, bigger wavelength. So notice I was oddly careful. I drew a slightly longer wavelength from the particle under that potential surface there. So that was on purpose. Okay. This is where it gets good. Uh-oh, now what? We just got faced with a problem similar to this. What happens? What happens?
Classically or quantum?
E minus B is what?
Negative.
It's negative. What's the root of a negative? Right. Therefore, K is, actually, what do we do? Okay, so let me, I'm running low on time. What you're going to do is you're going to do it this way. So, kappa, it's like big K, and the I's are gone. So you see what happens, I times I. Actually, I guess I should put like the minus there, and then I should put the minus here. It doesn't matter at all, a plus there, but I'm just trying to, if this K is really I times K, then Then I got I, which is minus, and then minus I squared, which is plus. Where kappa is actually redefined, B minus. So now it's real. Anyway, so that's the solution. What I've done here is I've just made some redefinitions so that I can eat the I up and make the I go away, and I make the wave vector. Remember, K is a wave vector. I made it real again. It's real here, but the I comes from the solution of the cube. And here, the wave vector is imaginary, so I made it real, and then I just ate the I. So I kind of done two steps at once, and I hate to do this to you, it's just kind of low on time. And so then you can see that these are simple exponential decays. So a wave function can enter a potential energy surface. So let's give this guy slightly longer wavelength. But so it has less energy. Notice I do the wavelength longer, but as soon as it gets into this potential surface, it just flatlines. Just exponential decay. It doesn't become such a good exponential decay, does it? That bothers me. It has to be perfect. There we go. That's an exponential decay. Okay, so there you go. So things, waves can enter potential surfaces. Next thing, just like this thing I just drew here. I see we've got just 1 minute left. Okay, let's say it's a step potential. God knows that's what you got on your homework. Okay, so this is accurate. Energy greater than V, it still continues on as a wave, just with less waviness. And energy less than V, it exponentially decays, doesn't get too far. Okay, and then of course the way to solve this, and to solve this, what you're doing is you're figuring out what the K's are. There's a K on the left side, and then there's a K on the right side. Because either it's less than the energy, because it's shaped off some potential, or in the other case, it's that it takes a different form, it's kappa. Okay, so I literally just only have a minute. So I'm just going to solve really quickly. At x equals 0, you have a boundary condition. So you solve flat potentials, solve with boundary conditions. And again, I'm praying, again, when I teach undergrad quantum, we've done this problem, so I'm really hoping you've actually seen this before. This is a reminder, and if not, that's awful. But what you had is on the first region, and you have the second region, and again, that's because they have different Ks. And what you assume is in region 1 at the boundary, the wave function will be the same at region 2 at the boundary, and then you have two cases, E greater than B and E less than B, where E less than B is the one that's interesting. Then of course you have the derivative has to be equal. So that's continuous and this is smooth. Remember, I think I mentioned, or it's in my silly textbook, wave functions have to be continuous and smooth. And, or they, technically, if a wave function does something like this, it has like a kink in it, that requires infinite energy. So it doesn't have infinite energy, so you can't have wave functions doing stuff like this. So that's why they have to be smooth and continuous. Okay, now to figure out how to describe the wave function, you're not looking for A or B, you're looking for K. Actually, sorry, in this problem you are looking for A or B, my bad. Any K is allowed. Sorry, I misspoke. But to solve, so normally these two are coupled equations that allow you to figure out everything, but the real trick is to take the derivative on the left and divided by the amplitude, and then the same for the right side. Derivative divided by its amplitude at the boundary. Now, again, I'm really just answering your homework question for the step potential. And then you can solve for A and B, C, but really what you want is the percent reflection is B squared over A squared. So when you're working this problem, we're out of time. When you're working this problem, you see the wave functions on the left. You know what the wave functions on the right are. Derivative divided by the functions, and you will be able to figure out what A, B, and C are. And notice that what the question is asking is, what's B squared over A squared, in case they're complex. Anyway, look, if I just blew your head off, we're going to have a review session tomorrow, okay? So, I hope I didn't blow your head off, but again, we got this class outside, we got to go.